Okay, good afternoon, everyone, and thank you, Trudy, and thank you, Mark, who's not here, for inviting me to give a talk here, and thanks to the department here as well as YCI. It's a real privilege to be here, and I'm delighted to do this presentation here. I thought I would pick as a topic trends and extremes in climate. And in part because these are becoming such not only the science motivation points, but also important points of information into policymaking circles concerning impacts, vulnerabilities, adaptation, and mitigation. So I thought I would discuss this I come from a physical science standpoint, but I think there's a lot of things to be learned in how physical climate has to give information and interact with the other disciplines which are seeking information on climate. You see my name up there, but I have to confess that only a small portion of this talk is really my work or work I participated in. A lot of it is really coming from all the other GFDL scientists, but I think together it would make a little bit of a coherent story on what we understand about the climate system in terms of looking at trends and the extremes. So I'll begin with what's kind of now a 5-year-old thing, namely the results from the IPCC 2007 report. But the trends or the indicators that were identified in that particular exercise were these various things: temperature over land increasing, temperature of the troposphere increasing, humidity increasing, sea surface temperature increasing, sea ice decreasing, ocean heat content increasing, snow cover and glaciers retreating. So these formed a good idea of the trends that we were seeing and that was assessed to be the state of the art knowledge back in 2007. So I'm going to actually elaborate more on some of these items and actually cover a couple of things that were probably not very familiar back then, but we now discern them to be part of the trends of a warming world. So picking up from 5 years ago and coming to my institution, particular GFDL, where we were in the 2007 framework was these pretty much the pictures that you see above here, or a couple of them. And we were also, so some of the results that fed into the IPCC, we participated in model simulations which went into those results. But since that time, two particular things have happened which have driven us in the direction of the arrows that you're seeing here. One is the resolution aspect. And the models that we had, and most modeling institutions had at the time of the AR4, were roughly 200 kilometers in horizontal resolution. And since then, the desire to get more information on finer scales has driven the science towards seeking models with higher spatial resolution. And you'll see where that has gotten us so far. On the other hand, there's also been a desire to capture more realistically the processes happening in the Earth system, be it atmospheric chemistry, aerosols, biogeochemistry, and so that has been another driver. Now, ideally, you would like to marry the two and come out with the highest resolution possible, the most complex system possible. But that may be a solution, but just from a very pragmatic viewpoint, it seemed to us, this is 5 years ago, that we got to march a little bit in a calibrated fashion towards this ideal goal of the highest resolution and the most complex model, and seek instead intermediate pathways whereby you're advancing in this direction and in that direction, and try to see what more can you learn relative to what it was 5 years ago. So let me go into trends part of my talk, and I'm going to talk about this model that we have, CM3 as it's called, coupled model 3. We've assembled it for the World Climate Research Program, CMIP5. Those are the model intercomparison experiments, and also they're feeding into the IPCC AR5. And in particular, I'm going to talk about this business of greenhouse gases versus aerosols. How have they changed climate, or what is our update on the knowledge concerning the relative effects of greenhouse gases and aerosols? So one of the things that I want to first describe in terms of the model details that we wanted to particularly capture was two things. And basically, these involve the short-lived species and their interactions with climate. One was the whole business of, shall we call it, gas phase chemistry, which not only contributes to climate, methane, ozone, etc., contribute to climate forcing, but also the air quality issues. Because one of the things that the questions were being asked is the impacts on air quality due to the same agents that force climate change. And then the other issue was trying to get at the whole aerosol-climate relationship, including the very sort of nebulous effect of aerosols in clouds, or aerosols interacting with clouds and altering cloudy skies, and what they do to things like surface fluxes, these mixed layer, deep ocean, etc. So we want to capture these two things, both of which pertain to the short-lived species effects. And so we basically came up with this model, which is shown here schematically, where this is the big box doing atmospheric chemistry in the coupled model, and fed into it are emissions of precursors of various pollutants, ozone depleting substances, which of course have their effects in the stratosphere, and then other inputs are the insulation, the well-mixed greenhouse gases, volcanic aerosols, and then of course you have the traditional atmospheric dynamics and physics components involving convection, etc. And then there were some change in land model and ocean sea ice model. I'm not going to go into details into all that. I'd be happy to address them after the talk. And these were some of the changes that now resulted. So basically, it was a very similar looking model that compared to last time, excepting there were more levels. And I'm not going to go into details, but there was an improvement in the convection scheme. And that's what it means when I just updated moist physics. And one of the things that you always want to inquire into is how good is a model doing with respect to present-day climate parameters. So since I'm going to focus on the aerosol issue, I decided to put these plots up, which shows a comparison. If you look at this particular plot, it shows a comparison of the optical depth in the model, aerosol optical depth in the model, versus measurements. Aeronet is the measurements. And this is the older model, which was circa 2006. This is a newer model, 2011. And the correlation coefficient is listed here, which goes from 0.54 to 0.68. And on the right panel, you see the comparisons. This is a relative difference with the Aeronet sites. And I think you don't have to look at the numbers, but there are brighter red spots and brighter blue spots than on the lower panel, which means that the lower panel has actually improved in terms of its simulation of the aerosol optical depth. And the correlation coefficient here may not seem like a big deal. It's certainly not a very big improvement, but it's going in the right direction. And the key thing is this was a model in which aerosols are not interactive. They were prescribed, calculated from an offline model, and then inputted into the climate model. In this one, it is actually interactive and online with the meteorology. So in that sense, this is not only doing a more realistic handling of the process, but is actually also improving the optical property simulation in the model. Another sort of comparison with observations is that of tropospheric ozone, and this happens to be 3 sites in India at different places in India, showing the seasonal cycle of ozone. And you can see the comparison between the red and the black is rather nice. It's very encouraging that the model is able to reproduce it, although there are still details that have to be captured, and it's not a completed story yet. All right, so what does this model give in terms of response to the various forcings over the 20th century for the global mean surface temperature? So what is plotted here in the black line is the observed global mean surface temperature anomaly over this period, which is 1850 to 2000. And there are 2 sets of lines here. Okay, ignore this. This curve is what you get if you ask the question, supposing well-mixed greenhouse gases, CO2, ozone, CO2, methane, N2O were the only gases forcing the system, what would you get? For the climate system, you'd get a rapid warming, which looks like this. And then you can ask other questions like what happens if you forced it only by tropospheric aerosols. Then you get a curve like this. And the green one represents the effect of solar and volcano. And the blue one is with all the forcings. Now, just to compare the blue and the black, which is the observed, you see that there is it's not exactly matching the observed. In fact, although the trend in the last 30 years is about similar, this really has a very large sensitivity to volcanoes, so that the model gets really depressed when it gets hit by a volcano. And then just for comparison's sake, so this is the observed trend over the last 100 years. This was what the trend was in the previous model, but it was, remember, a model which had lesser realism in our view than the blue one. But the blue one underestimates the observed, the other one overestimates the observed. So the good news is that you can use actually these two different models to examine kind of how different species under different assumptions have forced the model. But the kind of unhappy news is that it is not exactly on the dot, which you would have liked it to be. But nevertheless, there is the last 30 years, the warming is significant, just like it is in the observation. Now, so I'm going to actually now, that was a global mean. I'm going to switch to the tropics, and this is actually a simulation for South Asia for the different components. So this is the all forcing always means it's forced by natural and anthropogenic agents. This is if it was forced by well-mixed greenhouse gas only. This is tropospheric aerosol only. And the key thing, both in the global temperature as well as in the South Asian temperature representation, is this large opposite sign amplitude that you see for the greenhouse gas and tropospheric aerosol, which is very striking. That in the end, in the last 30 years, the greenhouse gas effects has certainly dominated over the aerosol effects in terms of temperature change, as you can see by the net result. But it is really interesting that the offset is actually become an important component driving the surface temperature. And this is looking more closely into South Asia for the different components. This is the all forcing, so that's kind of the result that is there at the end. The greenhouse gas only is, again, forget about the numbers, but it is strong warming, and this is strong cooling. And the volcano effects actually do add something to the end of the 20th century temperature change. So as far as the temperature is concerned, the story is very much similar to what was obtained before, even though the model's realism is supposedly has improved, but the result is pretty much similar in terms of aerosols offsetting greenhouse gases. Now I want to sort of dwell on the precipitation over the South Asian region. So first of all, looking at the observations, or I should say numbers culled from observations, and then trends have been formed out of that. So this is the June, July, August, September rainfall trend, millimeters per day over the 50 years. This is the CRU record. This is another record. I forget now where this comes from. And this is the University of Delaware, which is, these two are actually quite well known. And the fourth one is the Indian monsoon rainfall record. Now, looking at these figures, the thing that strikes you is there's a lot of areas in blue, which means deficit in rainfall, anomalies in rainfall, negative anomalies in rainfall. And the CRU, Delaware, and this data set actually show a very pronounced decrease, particularly in this north central Indian region, which is kind of the breadbasket of India. This is where most of the agriculture happens. And it's also a very populated region, so the economics of the region become very severe when there's a drought or when there's rainfall deficit. Now, the Indian monsoon rainfall is the only one which does not show a very strong negative trend, but there are lots of questions about how the trend actually has been evaluated using the discrete data from the different stations compiled in this particular plot. It's actually an unpublished plot, but nevertheless, it's the only plot which doesn't exactly, which doesn't give the same magnitude of decrease as this one, the other three. But by all means, by all sort of knowledge, it is well understood that there has been some decrease. I think the magnitudes are the ones that are probably in question. Now, in terms of model simulations of this phenomenon, this is the plot showing the effects of the various forcings on the rainfall decrease over the last 50 years. first of all, the observed trend, and in the background are the kind of curves, but if you look at just a linear trend, this is the observed, and all forcings is the red line here, so that's going like this. And then if you have greenhouse gas only, greenhouse gas and ozone, that goes like this. And then there's a natural, which is a yellow, which is going like this. And then the aerosol is the green line here. So first of all, it is actually striking that the aerosol curve and the greenhouse gas curve are opposite. The trends are exactly opposite. This one, greenhouse gas alone would actually cause an increase in rainfall there. And that's actually well understood from a lot of modeling studies done right from the 70s, which shows that the monsoonal area rainfall has to increase. And I'll tell you, I'll come to the reasons why. It's basically the simple reason is more moisture in the atmosphere in a warming world. But then the aerosol one goes in the opposite direction. And it's the sort of the red curve, which is all forcing, actually follows much more the aerosol trend than the greenhouse gas trend, and is very close to the observed, or reasonably close to the observed trend. So the most important implication is that the temperature changes show the greenhouse gas dominating in the net result, whereas in the case of precipitation, it turns out to be the aerosols. Yes?
Everything in, including soot?
Yes, everything. So this is anthropogenic aerosol. Thank you. Anthropogenic aerosol, which means we are having black carbon, organic carbon, soot, black carbon, organic carbon, sulfate, nitrates, and plus there is the aerosol indirect effect in which organic carbon, black carbon, and sulfate participate. So,
sorry, one more question.
Yeah.
This is regional, right?
This is South Asian region. This is this box. This is this box here.
So when you make the climate warmer, there'd be more evaporation.
Yes.
So this would have to be compensated by more precipitation elsewhere. Is that true? Or is this
Not quite evident. I actually don't know the answer to that, but it's not so evident that there is necessarily an increase somewhere else in the tropics. It may be an increase outside of the tropics, that I'm not sure. All right, so why does this happen? I mean, it's kind of why does this seemingly aerosol dominance in the precipitation happen? So we can search for an explanation by looking at this plot here, which is an indicator of the radiative flux perturbation due to aerosols. So what this is doing is comparing just the radiative flux change, including the fast physics. And it's a kind of a little bit of detail, but the basic point here is that the aerosol introduction creates a top of the atmosphere reduction of about minus 2 watts per square meter globally, and the surface reduces to minus 3.6. Now the surface reduces because there is actually less solar flux coming to the surface. And one of the things evident is the absorption of the atmosphere. There is a strong absorption of the atmosphere, but there's also a strong surface flux deficit. And notice that most of it, these blue guys are big chunks. Most of it is north of the equator. There's very little south of the equator. That's because there's very little aerosol south of the equator. Most of it is in the northern hemisphere. So just schematically explaining this, if you take climatology, and we can just consider, we can distill this down to two simple things, the Hadley circulation, the Walker circulation. So this is the Hadley circulation, this sort of latitudinal, and then this is kind of along the zone, tropical zone, the Walker circulation. So that's climatology. Now if you add greenhouse gases, what happens is the greenhouse gases actually weaken the Walker circulation. So you can see that schematically, they weaken the Walker circulation. But simultaneously another thing happens, that water vapor content in the atmosphere increases because you're having more evaporation. So that tends to moisten the atmosphere, which tends to then dump more precip. So that's why precip increases in a sort of a very simplistic fashion. Precip increases in the tropics in the greenhouse gas case. In the aerosol case, well, they actually tend to go in opposite direction in terms of the Walker circulation. So they kind of enhance the Walker circulation, but that's a small effect. That's not a very big effect. The major effect is the reduction in the Hadley circulation. And that occurs, again, sort of in a first order sense because you have a lot of deficit of flux, solar flux, hitting the northern hemisphere southern hemisphere practically is unaffected. So the reduction of the flux in the northern hemisphere essentially lessens the diabatic heating in the northern hemisphere. Now, one thing that we noticed in our model is although most of the aerosols are located in the continental regions, and a lot of it, of course, is over Asia, but this is not just a local effect. This is sort of an entire northern hemisphere, southern hemisphere asymmetry, where the northern hemisphere is cooling down because of the surface flux. Not cooling down. Northern hemisphere has less diabatic heating. Southern hemisphere has more. Southern hemisphere has no change. So that tends to decelerate or reduce the Hadley circulation, which then reduces the precipitation. And so this is the composite picture, which is pretty much dominated by whatever is coming out of the aerosol story. So the greenhouse gases don't have the analog to the Hadley circulation change in exactly the same way. There is a Hadley circulation change, but it's much smaller than what the aerosols from pre-industrial times to present day appear to have introduced. And now I want to sort of harp on this a little bit more, this Hadley circulation change arising out of north-south asymmetry, not northern hemisphere, southern hemisphere asymmetry. This is actually another model result, but it goes way back. This is actually work that was done with a pretty ancient model now called the Manabe climate model, done about 20 years ago actually, or 16 years ago, where that time we didn't have very good formulation of aerosols. The model, we just did a simple experiment where we argued, let's just do an experiment where greenhouse gas plus an albedo change due to a proxy mimicking sulfate aerosol is equal to 0 in the global mean, but all the aerosol is in the northern hemisphere, greenhouse gas is global. So what you would get when you have global mean forcing of 0 is you don't have any change in the global mean temperature, but you do have northern hemisphere not warming so much, southern hemisphere warming a lot. But the most interesting thing that we noticed was the precipitation, where if you did just a greenhouse gas experiment, that is this curve here, so basically not much change in the precipitation. Albedo kind of gives you this very sharp drop where you have decrease in precipitation just north of the equator, increase in precipitation just south of the equator, and the combination, whether you add the responses individually or do a response to combined forcing, gives you pretty much the same result. So in this experiment also, it was essentially the northern hemisphere, southern hemisphere asymmetry in diabatic heating that was pushing the ITCZ especially southward. Yet another experiment was done recently with pretty much the similar model as I showed earlier on, but coupled to a mixed layer rather than a full ocean. And again, the same effect happens, where the gas effect on precipitation is this, the aerosol effect is this, and the combined effect gives the same conceptually the same striking result, which is that the north of equator it is precipitating less, south of the equator it is precipitating more. And here I have to add that these are actually turn out to be not results dependent on any model, because these are results that have also been obtained in the context of the LGM simulations, where you have ice sheets in the northern hemisphere, and basically they reflect more, so they're causing a reduction in diabatic heating, and that tends to have the same effect. It pushes the ITCZ southward. And essentially the same effect happens in an experiment that I just saw recently that Ines Fung showed, where she was doing an opposite thing, where she was doing an experiment on afforesting the temperate latitudes in the north. So you're actually now adding deciduous forests in the north. It's an idealized experiment. But one of the things that happens is that you reduce the albedo. Now in this case it's going the other way. The albedo is decreasing in the northern hemisphere. So if this theory were to be valid, you would expect the ITCZ to move northwards. Yes, and it does happen. That's what I saw a couple of weeks ago from her model result. So it seems to hang together that these asymmetric diabatic perturbations caused by any forcing agent, not just aerosols, seems to have a very discernible effect on tropical precipitation, which I think is something to sort of analyze more in detail. Now, there's another interesting aspect to this, which happens if you are looking now into the future. So now into the future, so here we are 2000, and if you look in the future, these are all the different scenarios. So this is the historical radiative flux perturbation, and then you consider the different scenarios, 2.6, 4.5, these are different amounts of CO2. So they go the conventional way in terms of radiative flux because your greenhouse trapping is increasing. But the scenarios about aerosols, goes this way. So here we are in 2010 something, and the aerosols are supposed to decrease, which is why the radiative flux perturbation is fast approaching zero. So aerosols are decreasing in the atmosphere, CO2 is increasing. So one of the things that happens at temperature change is that because the aerosols have been holding like a thermostat, they are being offsetting greenhouse gases, suddenly you remove that, then you get warming. So this difference that you see here, and this is for a particular scenario, this difference you see here in 2100 is because of the fact that the aerosols were drawn out of the atmosphere. Yeah. Why are they going to decrease? That's what the scenarios seem to think based on air quality and health reasons. Countries in Asia especially are supposed to decrease. I'm sorry?
Because human behavior is going to change.
Because human behavior is going to change. That's the projection. So if that is so, then you would see actually an accelerated warming more than just due to greenhouse gas alone. And in fact, that warming is exacerbated in the mid-latitude northern hemisphere, including the Midwest United States. It seems to get a large bang out of reduction in Asia. But the more, I mean, this is something that is well understood, I think, by now from even the previous IPCC results. But the precipitation one is an even more interesting thing. Now, this is an extension of the previous curves on precipitation, but going beyond 2000. So, and this is for a particular scenario. I think this was RCP 4.5. So, here we are in the before 2000, where greenhouse gas increase is going like this, and this is with all the forcings, and this is due to aerosol only, showing how the aerosol has controlled the precipitation up till now. But if this assumption that we've been making about the asymmetry between the two hemispheres and tropical precipitation is even partially correct, then what should happen as the aerosols go to the atmosphere is that this has to go back up, because now it has to be dominated by greenhouse gases if the anthropogenic aerosols are supposedly going out of the atmosphere. And so that's an interesting test. I think it's going to be very interesting to see how this really works out in the real world. If it doesn't, we have to go back for another explanation for the 20th century, but this is sort of an intriguing challenge that lies before us. Now, just generalizing on precipitation trends, another thing that I think we have to be looking for in terms of detection attribution is just the overall character of precipitation change as we move into the 21st century. So at the end of the 21st century, the projections from the last IPCC are that these are the trends you should see in all the seasons. The southern portion of US would see a deficit in rainfall, and the northern side should see an increase in rainfall because the whole moisture process is moving poleward. There's a northward movement or a poleward movement, and so you should see that. And so this is actually another sort of precipitation pattern that we have to be cognizant of, which is kind of irrespective of aerosols, because this is something going to happen when greenhouse gases become so much in terms of forcing, then this pattern should again happen. All right, let me now jump to a different topic, change the flavor here to talking about extremes and what can we comment on the extremes in terms of recent developments in at least the scientific modeling science. So there are three things I want to take up: Atlantic hurricane activity, heat waves, and just the intercontinental transport of pollutants. So first of all, I want to go back, rewind the clock to 3-4 years ago when we are still dealing with the CMIP3 and AR4 results. One of the experiments that was done was where there was a sort of a downscaling of sorts, where results from global climate models were downscaled into a high resolution model. So essentially global models were downscaled to domain of this size, and then that was downscaled further to hurricane model size, which is of the order of about 8 kilometers. So you're doing like 2 downscalings to see if you could simulate the tracks of hurricanes using outputs from global climate models. So basically that would be inputting the sea surface temperatures and the large scale winds around this box, and then this box supplies the winds to this box. And of course these are run for short time periods so that you're not violating boundary condition constraints in any way. So what this gave as a result was the following. So this was done with a bunch of models, outputs, including Hadley Center, NCAR,
GFDL, Max Planck. And so the story out of this, which came up, which was published in 2010 in Science, was that the changes in hurricane frequency over 21st century would be something like this, where category 1, 2, 3 hurricanes decreased in terms of the number of storms per decade. But the severest ones, 4 and 5, increased. So this was actually quite an interesting result, that you had the severest category increasing in number, but the less severe categories actually decreasing in number. So actually the total number of storms really showed a decrease, but the most severe ones showed an increase. So this is about 4 years ago with model outputs which are in the 200 kilometer resolution range. Now, of course, we have been able to develop high resolution global models. And one of the tests for these models, not a sufficient test, but nevertheless a test, is how well are they able to simulate orographic precipitation, because orography gets resolved as you increase resolution. So consequently, you should expect better results. And this is kind of a set of results that came out very early in the development of high resolution models at GFDL, showing comparison with observation. So this is actually, it's not exactly observation, but it's data put together from observations. This was a model that was there in AR4, and you can see that, and these are models which are forced by observed SST, so that's why you get the precipitation in the right place. But it's a pretty diffuse pattern that occurs in the lower resolution models, and as you crank up the resolution, this is a 50 kilometer model, and this is a 12.5 kilometer model, you actually start to get really better and better representations of the orographic precipitation. And this is Western US and DJF. Of course, this is something that is not surprising, because people have known this from simpler modeling studies, that if you increase resolution, capture the orographic envelope, you're going to do better. But now we've applied this to other parameters, other variables. So this is the mean northern hemisphere sea level pressure. And what you're seeing is the range of results from the AR4 models, including the GFDL atmospheric model, which is in green here. And then the higher resolution models. So this is 50 kilometer, and this is 25 kilometer. And actually, the 25 doesn't go down. 25 goes back up for reasons that we don't understand. But this is the annual. This is the various seasons. But by and large, relative to the range of the AR4 results, the higher resolution actually seems to be improving things, at least in terms of this variable. And we looked at others like 500 millibar geopotential height. So this actually encouraged us to go further.
Sorry,
Yeah, sure.
last slide. Is that an error in a weather forecast, or is that an error? What's the nature of that error that you're?
So this is okay. So this what you're looking at is the model forced over the, I think it was a 20-year period, 1982 to 2002, or 85 to 2005. And so you're forcing it by the NCEP climatology, the SSTs. And then you're looking at the NCEP results for the sea level pressure. That's the way I think it worked. And so this is a comparison with whatever observation there is of the sea level pressure.
No, I'm just a little bit confused, because sea level pressure is a measure of how much air there is in the atmosphere. So
Right.
unless it's a particular forecast or something, it's hard to know what that error. You can't be misrepresenting the amount of air we have. So it's got to be some other kind of an error measure, isn't it? Sorry.
No. I'm trying to think. I was thinking of this as a climatology and then comparing with the climatology. So you're forcing the model and with the climatological SSTs, and then looking at what the atmospheric pressure is.
Yeah. Okay, go ahead.
I think I'll try to think about it and get back to you. Okay, so this has encouraged us to look at further, looking at it further. So what this part is showing is the 25 kilometer model, and this is actually simulating North Atlantic tropical cyclone frequencies or activities number of storms is here, annual number of storms, and then this is a plot versus year. And the red are the observations, and blue is the model ensemble mean. And the way that this modeling work was done was initialized as of 1st of July. So you're initializing the model on 1st of July, including the anomalies, and then just letting them, and then keeping the SSTs fixed. SST is not changing. And then you just let, well, SST is changing, but sort of we're doing the annual cycle, but with the same bias as of 1st of July, or say anomaly as the 1st of July, and then letting the model run and do its thing and generate storms. What is sort of very remarkable is the agreement that you get in terms of the number of storms generated by the high resolution model. We didn't get this when we were working on with the low resolution model. We never got a result like this. And this actually is the 50-kilometer version, but the 25-kilometer actually does a very neat job. And in fact, the statistics appear on this plot here is the same plot as before, excepting now you're seeing the orbs in black, and the red is the mean with the bias removed, and the pinkish dots are the actual mean. So basically there's no difference between the red and pink excepting for a small overall correction bias, but they're pretty uniform throughout. Now the correlation coefficient for the entire period in terms of number of storms is 0.88. That's just unbelievable geophysical thing, that you can get such a high correlation, and over the last 10 years it's even better, it's 0.94. Now the thing that we suspect what is capturing this is really sort of two parameters which seem to be very fundamental to determining whether or not there's a cyclone in the Atlantic or a tropical storm in the Atlantic, and that is, one is the tropical basin temperatures, mainly the Pacific sea surface temperatures, and the other one is the Atlantic temperature. The two together seem to, as long as you capture them well, which you can, if you're using NSEP observations, then it seems like you can actually march to a result like this, which is really very, it doesn't say anything about tracks, landfall, and so on. Those are different things entirely, but the frequency it seems to be pretty well captured by this. And this has led to another set of downscaling experiments where outputs from the global models in the CMIP archive are inputted into this model. So the SSTs from those models are inputted. It's run the same way. And what you see here are two sets of results, one for CMIP 3, and this one is a newer result for CMIP 5. And these are various models in CMIP 3. And you can see that there's not much you can say about what the projections would be at the end of the 21st century. It seems a mixed result. And then you go to CMIP 5, and now these are only the GFDL models. We haven't gotten around to the other models, but they're for different scenarios here. And this seems to be giving a different picture, both from our models, which are the coupled model that I showed earlier, and then a different class of models called the Earth system models, in which the carbon is interactive with climate. But they seem to give, well, if you can, 3 out of 4 seem to suggest an increase in storms, but that is kind of an off-track number here. So we hope to do this with all the other models, but this seems like an interesting study, or an interesting set of results for the projections in the Atlantic hurricanes using high-resolution models. Now I'm going to switch gears again to come to heat waves. So with the same model, because of the resolution it affords, you can actually go into the topic of heat waves. And what this is showing is a comparison from 1982 to 2008. The model temperature over the Midwest. So this comes out of the atmospheric model, 50 kilometers resolution, forced by SSTs corresponding to this period, 1980 to 2008. So you got a very good representation compared to the observations, although the amplitude is a bit too large. And accompanying that is the drying that you see, and the model again has a little bit as a sort of almost like a uniform result across the entire eastern half of the US. The observations don't have that kind of an amplitude, but nevertheless there is a coherence that's evident. And this is actually related, it can be tracked to meteorological conditions. If you look at sea level pressure and surface wind from model and observations, and the locations of these maxima and minima in the 500 millibar geopotential height, this pretty much squares up with the observation and sets up a kind of coherence that then it suggests that you can actually go forward and quantify the so-called heat wave. Now, heat wave is defined in a certain way, and I actually exactly forget the technical definition, but it involves a lot of parameters, such as it has to be above the anomaly has to be above a certain temperature for 3 days in a row. It has to hit the 10th percentile in warm temperature and so on. But nevertheless, just accept that what I have is really the real heat wave defined by WMO.
Rama,
Yeah.
why are we confining this to Midwest?
No, I'm going to other areas. I'm starting with the Midwest because it's an easier place to explain things. But this has been done for other regions and around the globe. It's been done for Europe and Asia too. And in each case, the kind of picture that I showed earlier, this one, you can sort of really discern it everywhere. Wherever there is a so-called heat wave, this is preceding the definition of the heat wave. All these conditions. This happens in all the continents.
Now, these conditions, they are not cyclical also, which will be through the 21st century.
They are not what?
Cyclical. In other words, up and down.
Oh yes. They are, no. This is the past. This is the 1982 to 2008 period.
Okay, so from this, you're going to project.
Yes, I'm showing the project. What happens? But first, let me go through the present. What happens? So using this, then you go and do time slice at other points. Like we took the 2030 SSTs from the coupled models, 2090 SSTs, not 2070s SSTs from the coupled models, and again drive the high resolution atmosphere to get similar statistics. Okay, I'll come. You can ask a question 3 slides later if you want to ask the same question. Okay, so now this is what is happening in the 1971 to I misspoke. It was actually 71 to 2000. So for that Midwest area, so this is the severity, which I think is the extreme in anomaly. And then this is the duration of days. This is how the sort of number of heat wave days per year are arrived at. You have duration in days, you have number of events, such events per year, and you multiply the two, you get the number of heat wave days per year. And this is the observation over that same time period. So it is this kind of comparison between model and observation that we are taking to establish a basis for looking at the future. And this column represents the period 2040 to 2070. So basically over this period, the SSTs from the coupled model were input into the high resolution model. And so by the same analysis of the meteorological events, you get at a duration which has now increased, the number of events per year has increased, so the number of heat wave days per year goes up by a factor of about 3 compared to the present period. And then when you go to, so this is a ratio. This is a ratio of 2041 to 2070 versus 71 to 2000, and you're increasing the number of heat wave days by a factor of 4. Now, when we look at other regions, you actually tend to find a coherence in the manner that's indicated here, where the colors are matched up. You tend to see a coherent pattern when you divide up regions in this manner, in the observations, and then you look at the model simulations. That's what the coherency appears as. And then so you can do a similar analysis just like for the Midwest. The Midwest results are here: duration, number of events per year, and heat wave days per year. You can do the same thing for each one of these regions, all the way from western to the eastern US and even into Canada. And so everywhere, you actually get a factor. This is the ratio. You get a factor which is at least 3. So it's 3 times more heat waves per year, heat wave days per year compared to the present. And if you look at it sort of again in the 0th order, what is happening is the warming of the surface, North American land surface warming, is essentially by 1 degree gets you 100% change in the number of heat wave days. That's how it scales as. So every 1 degree centigrade increase is giving mean summer increase, summertime 1 degree centigrade increase is giving you a 100% increase in the heat wave days per year. And I didn't add the other regions like Europe and Asia to this. They are in my slides. I can show them later on. But basically that they also give the same kind of result, an increase in number of heat wave days per year, which is at least a factor of 2 greater in the 2040 to 2070 time period.
What happens in the southern hemisphere?
Good question. It is not as much as a factor of 2. It's less than a factor of 2 in the South American and the South African regions. I don't know about Australia. That's, we should look at Australia. Australia must be more, but northern hemisphere is kind of showing, all the land masses are showing pretty uniform factor of 3 or more increase. Okay, so now my final example is actually climate chemistry. So in this case, again, the high resolution model was used in a slightly different manner. The 50-kilometer model was used to, which is this bottom panel here, was used to, in conjunction with chemistry, a full chemistry module as I described earlier, and the model was essentially nudged to global forecasting systems U and V fields. And then with full interactive chemistry, what was done was to find out about the transport and the fate of pollutants during a particular time of the year. Now this time scale was this period here, the month of May 2010, when there was actually an experiment performed by NOAA called the Calnex experiment along the west coast of the US. Basically went all the way from kind of San Francisco, well, San Francisco was here, and so it went from almost northeastern Pacific through San Francisco through to Los Angeles. And there was extensive measurements, both from satellite as well as from balloon sondes and other ground-based measurements. And the same, so they used 2 models. One was the coarse resolution model that I talked about before, which had the full interactive chemistry, and the other one was this high resolution model, 50 kilometers. So one of the things that the model does, this is now the high resolution model, is shows this intrusion of ozone coming from the stratosphere, and you can see that it actually goes all the way to about a couple of kilometers. That's a large chunk of ozone. It's 100 ppbv. And so the key point, in connection with this talk, is really the comparison of this with the observed measurements. So this is showing the balloon observations, and this happens to be a particular day in that sequence, May 28th. And so you can see the measurement sites. This is sort of all the measurement sites, and they are listed here. And this is a transect versus altitude, and you're seeing the blob of ozone coming down on that day, or this is a picture on that day. That's the coarse resolution model, which is wanting to, spin it off, but just doesn't sort of get very, very sharp. Whereas the high resolution model seems to do better in this regard in actually getting it down to lower altitudes. And the interesting thing about this is that you had 100 ppbv just about 3-4 kilometers above the surface in Southern California, in a densely populated region. I mean, that's a really, if of course this was a single event in the course of this campaign, but if those are events which are happening more, if they happen more frequently, then that is actually going to call for reassessing air quality, surface air quality in these densely populated regions. That's really a very, very large chunk of ozone. Okay, so that was my third example of an extreme. So let me go to my summary slide. I really basically want to again harp on 2 particular points, one concerning the trend, the other concerning the extreme. So in terms of the trend, I think we've been so used to looking at surface temperature changes that, and I think that's a pretty nice record of how well we have done in trying to simulate 20th century global mean temperatures and even continental scale temperatures, surface temperatures. But I think the next order of business is actually look at the regional precipitation patterns, particularly those induced by aerosol effects in the South Asian region. Now, how robust are these results? What are the different models giving? So that'd be interesting to look at. And then, of course, the fact that the trend would be reversed in the near future if these anthropogenic aerosols were just not there. And along with that, I'll also sort of cite the spatial movement in terms of precip anomalies as we move towards a more greenhouse gas dominated world when the precipitation should move poleward. And then in terms of the extremes, I think it's encouraging that these high resolution models with more realistic physics are actually capturing reasonably the extremes, or what we or maybe more appropriately defined as anomalies from the mean, departure from the mean in terms of severe impact events. And that is certainly something that is going to be important when when people interested in regional impacts are asking for climate information. I think we have a very good tool or very good basis to actually set about answering that question. So I'll stop there and I'll take questions. Thank you very much.